Well, good morning, afternoon, or evening. I'm Professor Rios. Welcome to week 7. This week, we delve into the tricky, touchy, funky subject that is climate change. I'm sure you've heard of it. Bear in mind, there is another lesson slide packet that I include in the weekly folder on Brightspace, and that one is from another course that I teach that has a little bit more current information. Bear in mind, unlike other things about physical geography, climate change changes quickly. Haha, funny, right? So I had to add other information because the book has some data that is, well, dated. So bear that in mind. This is an update to the existing presentation to add some new information and some updated slides. So having said that, let's get going to the presentation. Again, there is another slide packet that you can look at. There's no video for that one, but you can go through it at your leisure. All right, so climate change, it really ties together areas of the world that are very far from each other, like the ice caps, Greenland and Antarctica. Again, these are the different lesson objectives. You can look at them on your own. Just to give you a sense of significant climate anomalies as of 2023. So obviously an anomaly is something that is different from the norm. So if it's supposed to be 90 degrees for a high and it's 99, well, that's a 9-degree anomaly. That's really all that means. So here you get a sense of it's not just the United States or Europe or Africa or Asia, it's sort of everywhere. And they include droughts, floods, fires, cyclones, whether they be winter or tropical cyclones. All right. So let's begin with Greenland, an example of an area that is affected by climate change. Think of Greenland and Antarctica as radiators on the Earth. So this is the number or the cumulative number of melt days. So there's a melt season in Greenland, and it's usually somewhere in the May through September time period when the sun is up a lot. That's when the temperatures up there can get warm enough for it to melt. So where you see white melt never happens. You have to think about the fact that Greenland can be up to 10,000 feet in height. That's a big chunk of ice. So in 1981, notice the difference from then to 2001 to 2021. In 2021, the area that remained without any melting, meaning it was well below freezing, much smaller than it was in 2001, which is much smaller than it was in the year 1981. So that has implications. Once that water melts, it goes into the Atlantic Ocean. So it literally adds to sea level because it was once on land. Now it's been basically given to the oceans. Here's another example of mass loss for Greenland from the year 2002 all the way through 2022, with a little bit of data missing in the year 2017 and 18. But there you get a sense of what you need to focus here is the trend. There's been some ups and downs, but bottom line, the net trend is downward from the year 2002 as of when these data were collected. Here's a number of cumulative melt days for the years 1992 to 2021. The trend isn't huge, but you definitely see a difference between in the early 90s, it went up again. There's been a few ups and downs. 2012 still the year with the most melt that took place. And you may or may not remember, but that was a remarkably warm winter in New York. If you remember that year, you may not. But in 2012, we had 90 degrees in New York, in Orange County, in March. That's unusual, clearly. So that was a particularly warm year where there was quite a bit of melting that took place. But bottom line, if you sort of average it out, it comes to about a little bit over 22, 23 in terms of square kilometers. Uh, I'm sorry, number of days, my bad. My number of days. Just to give you a sense that climate does indeed change, this is from Antarctica. So this is fossils that are found there now. Those are ferns. So it gives you a sense that it hasn't always been as cold as it is now, meaning the ice that you find there, clearly it was warm enough to support vegetation. And here's a sense of, from 1941 to 2004, although that's already 20 years ago as of the making of this video, it just highlights how over about a generation or two, a landscape can change dramatically to the point where now a forest grows where once there was nothing but bare rock because it was so cold. This is the west coast of Greenland. So this is, imagine zooming out or zooming in rather into a specific small area of Greenland near the coast. And there you see the islands and the different fjords and the little icebergs that break off. Notice how dirty the ice looks. This is ice that is very chunky. It's very slushy. And you have to really, really head uphill, meaning towards the center of the ice before it becomes white enough. But all these little pools of meltwater, they're like lakes on top of ice. So it's a lake with a bottom of clear, glassy ice. And oftentimes what happens is when there's a crack in the ice, it all drains into it. And so it's draining into the ice mass, causing things like tunnels. It becomes like Swiss cheese in a way. So it's not, it looks solid, but it's not. It's particularly chunky, crumbly, full of holes, full of air pockets. So climate change, we're going to look at the idea of climate and environmental change. So the idea of natural versus anthropogenic, that word implies human caused. Look at some of the data, some of the short-term versus long-term climate change options. So climate change is the temporal variations, either months to millennia and longer, of the ocean atmosphere system. So here's looking at data from 1850. So this shows you that the global average temperature all the way through 2023 shows that 2023, as of the making of this, is the hottest year on record, surpassing 2016 by quite a bit. And many people believe that more hot years on record are on their way. Stay tuned. Natural climate change and can be short or long term. Short term could be radiation, atmospheric dust, volcanic eruptions can do this in the short term and in the long term. Long-term changes, the Earth-Sun relationships, orbital parameters, ocean variations, and of course, extraterrestrial impacts. That means asteroids. So if you look at climate change, and this a little bit dated, obviously, it only goes through 2010, but it shows you that if you go back in time, in the 1500 to about 1800, there was this thing called the little ice age. And then there was a period before that, going back to the year 1000, where that's called the medieval climate anomaly, meaning it was warmer. And so you, even within the relatively short time record, you find these distinctive differences, either cold or warm. During the little ice age, places like England, which are not known for their particularly harsh winters, would have the rivers freeze. where people could walk across. There is historical data that shows that in the 1800s, when West Point, not that far from Orange County Community College, when West Point was just opened recently, or had just opened in the early 1800s, cadets would sometimes walk across the river from West Point to, what is it, Cold Spring on the other side, or Beacon? I don't think it's Beacon. Beacon's further north, but Cold Spring. Why? Because the river was solid enough that people felt comfortable. Perhaps that wasn't maybe a great idea, but the fact that they could do it signifies how different it was even as recently as the 1800s. I wouldn't do it, but people apparently did. Again, bottom line, it's all about radiation, whether natural or human enhanced. If more energy is coming in than outgoing, you heat up. If there is less incoming than outgoing, then the earth cools down. And in the end, you want to achieve some kind of balance. You want to be somewhere around zero. It is never perfectly so. There's always a little bit of warming, a little bit of cooling. And if you sort of average all that up, it comes out to some sort of happy medium. Climate change and feedback mechanisms. So there's no single cause of climate change. There's lots of feedbacks, and a feedback is, here is the idea of you have more solar energy, higher temperature, less snow, so the earth is darker, so you absorb more light, so it leads to higher temperatures, which can reduce more snow cover, leading to this, leading to that, leading to that. This is called a positive feedback. It builds on itself. Now, this can lead to a volcanic eruption, less sunlight, lower temperature, more snow, higher albedo, less sunlight, lower temperature. Get it? And it kind of feeds on itself. So these are feedback mechanisms. The idea of paleoclimatology. So anything paleo, like paleo diet, which I'm sure you've heard, right? Diet of the ancient humans. Well, this is climate of a long ago. These are studies of past climates using what are called proxies. And a proxy is an approximation. So there's no data going back 1,000 years or 2,000 years or 10,000 years. So how do you reconstruct it? Well, you can use things like tree rings. When trees have thick rings, that means it was a warm, wet year. The tree grew healthy. When the rings are really, really, really thin and you can barely see them, it may have been a stressful year for that tree. Maybe there was drought, no rainfall. So you can use tree rings, as we just mentioned, sediments, fossils. The big one is ice cores, and to some extent, human archives. So in terms of ice cores, you literally, it is as simple as it sounds, even if it's complicated to conduct. You go to Antarctica or the South Pole, Antarctica or Greenland rather, and you literally drill. And you drill kilometers worth of ice and you pull it up and you catalog it. And you come up with, you test for different chemicals, carbon dioxide, methane, dust, volcanic ash. And doing that, you can reconstruct it back in time. So with ice cores, you can go back roughly about 800,000 years, reliably. Anything beyond that, you have to look into rock, but we're not getting into that in this course. Okay, and so you can figure out how much methane there was in the atmosphere, how much carbon dioxide, and the temperature. And you can sort of see the relationship between peaks in these gases and peaks in temperatures. But notice some of these spikes are pretty sudden, they're pretty remarkable. And right now we're sort of headed towards a peak, when in reality we should be heading towards a dip. So there's sort of that human component that we're sort of having to account for. And again, a little bit of a, when you think about this graphic here, we're talking about years before the present in the x-axis, temperature in the y. So again, notice relatively stable, right? No huge peaks or dips. And then boom, you have this sort of like back in time when there was a significant dip in temperature, a spike before that, and then reliably cold before about the year 13,000 or so. Now, if you go back in time in New York, we were covered by ice. New York is a glaciated landscape. Orange County, Rockland County, anything north of the city is glacially carved, which is why if you look at mountains in New York, whether they be the Catskills or the Adirondacks, they're not sharp peaked. They're sort of rounded off. And that's a result of the ice. Think about the lakes, the Finger Lakes in New York. Many of the lakes you find in Orange County, Rockland County, Putnam County, Westchester. These are all sort of glacially carved landscapes. Ice cores, again, you can, if you think of an ice core, here it is. Notice how some of it is light, some of it is dark, and each of those layers is like a tree ring. And sometimes they contain lots of CO2, lots of methane, and you can sort of make that relationship tell you something about what the climate would have been back in time. Sediments, different, the shells that make up all these ancient and current sort of like little animals that you can find, and you can examine the carbon and the oxygen in these, and they tell you something about the age of, I'm sorry, about the climate that they lived in. Perhaps the certain type of oxygen you find would have been found in warmer climates versus colder climates based on the combination of that. The Human Record Archives. This is called Hunters in the Snow, 1565 painting depicting a much colder England, what we call the United Kingdom today. This is not what the United Kingdom is like now. I mean, they do get snow, but it's not to the extent where you freeze lakes and water fountains. So this tells you something about culture then. They were sort of used to this kind of winter scene in a place like the United Kingdom. Again, where that's not the case nowadays. So hurricanes, how does climate affect the idea of hurricanes? Each hurricane is very costly. It affects infrastructures, insurance, oil and gas, major US ports, economic nodes. So they definitely have an economic consequence when they do happen. And if you think about the idea of hurricanes and carbon dioxide and how does that all fit in? While this is dated as of 2024, the key to remember here is that it is increasing at a rate of 2.3 parts per million per year. This is called the Keeling curve. And I may have mentioned in a previous lesson that the ups and downs are caused by the canopy either growing or being shed in the fall in the northern hemisphere. When there's lots of trees with lots of leaves out, carbon dioxide dips because there are more trees in the northern hemisphere. And when the trees come up with all their leaves and it's springtime heading into summer, then carbon dioxide, dips. And then when the trees shed all their leaves, it actually rises. So you get this very distinctive sawtooth pattern. But in the end, you'll notice that each year's high is higher than the previous. So the increase of 2.3 parts per million per year. And think about the idea of a sea level rise scenario. Think about places like Newark, like LaGuardia, like JFK. So we're talking about three airports, three economic nodes. Think about all these different places in Long Island that would be effective. Staten Island, many of these sort of coastal cities that face New York City. Sea level rise is a reality. It is going to happen, even if we magically went carbon neutral today, because the carbon that was released years ago is still in the atmosphere, hasn't been scrubbed out. So as a result, that is going to continue. So this is one of the more, sea level rise happens in the span of millimeters a year. So that may not seem like a lot, but over 10 years, that begins to add up. Oh, now it's an inch or two. And over a decade, it might be 3 to 4 inches. And while that may not seem like a lot in relatively flat areas, that becomes a big deal. A big deal. So what are some of the consequences? Obviously health effects, agriculture, the idea of sea level rise, we already talked about, economic impacts, and at the very bottom, regional instability. So the next slide I'm going to show you, it's truly dated, but it's remarkably still on point. And that would be this. This is something that was in Fortune magazine in the year 2004. And yet it is as applicable today as it was back then. The idea that abrupt climate change may well occur in the not too distant future. Back then they were referring to probably now, but think about places that are being sort of flooded out. Think about islands in the Pacific that are the ones that are feeling the effects first. Like if you live in Kansas, sea level rise means nothing to you, right? If you live in the Alps, obviously. But if you live, the majority of people live near the coast. All the big cities are near the coast. Think about it. London, New York, Boston, Philadelphia, Charleston, Miami, Houston, San Francisco, Los Angeles, San Diego, Beijing, Tokyo, Manila. I mean, you can just go on. There's literally dozens and dozens of cities that are all at or near the ocean. That's just the way humans develop their coastlines. Mumbai, Bangladesh. And as a result, this is probably the most significant aspect of climate change, even more so than temperature. Short term, again, we talked about volcanoes, changes in solar output. So volcanism can be a big deal. I love this image, by the way. I don't know if you notice it. It's one of my favorite images ever because there is this massive volcanic eruption. Pinatubo is still the biggest eruption to hit Earth in a very, very long time. And yet here's a farmer and his ox just plowing the field like it's no big deal. Always struck me. That'd be the last thing I want to be doing. In any event, when Pinatubo erupted in the year 1991, the temperature of the Earth fell by about 7/10 of a degree. And you'd be like, so what big deal? It's not that much. Oh, that's a lot, especially in less than a year. So the Earth cooled. That's a typical response of volcanoes. Earth usually cools. It's not just ash that blocks sunlight, but it's the chemical reaction between sulfur dioxide and water, which basically blocks even more radiation. Solar radiation, the idea in insolation changes. Remember that term, insolation, incoming solar radiation. So here's a sunspot, here's Earth. That's how big they are. And solar activity goes in cycles. Every 11 years, there's a peak. Every 11 years. It's one of those very repeatable periodicities in nature. And we're about to head towards the 25th cycle, which will peak in the year 2025. Okay, so maybe you're watching this after that, but as of right now, we still haven't reached it as of the making of this video. So when there are more solar, when there are more sunspots, the sun is more active. And so that in turn has a net result in terms of temperature on Earth. And if you go back further in time, there is a period when solar activity was very weak. This is called the Dalton minimum. This corresponds with a little ice age to some extent in Europe. And then the Maunder minimum, which goes back into the 1600s. Remember, these were first recorded by Galileo long time ago. And so solar activity was really, really weak for quite a while. And this corresponds to a relatively cold period on Earth. So let's look at long-term. Again, any systematic change in long-term statistics of climate. And you have to sustain this over a long period of time. So think about how humans can impact this: pollution, urbanization, deforestation, and the increase in temperatures. You think about the idea of losing ice mass. A glacier that was once like this, it has significantly retreated back. And again, looking at the temperature record, this is the instrumented climate record going back to 1850. So this little window is this little box in this record, going back to the year 1000, roughly. And this box is this little box here, and this goes back to about 18,000 years ago. So roughly glaciation ended around the year between 11 and 12,000 years ago. And then we began to warm up to where we sort of are today. But keep in mind, we're still technically in an ice age because we still have two rather large chunks of ice on Earth, Greenland and Antarctica. We're not quite to the point where we have gotten rid of those. If we do, things would look very, very different on Earth. So this is a way of looking, again, this is the instrumented data record. This is reconstructed using those paleoclimate processes. So Milankovitch, this fella, he is basically a person who said he combined variations in solar output based on orbital parameters, meaning the relationship between the Earth and the sun. So the orbit of the Earth around the sun is either almost a circle or it's more elliptical. That is called the eccentricity. And if it's more elliptical, at one point you're relatively close to the Earth, and at another point you're kind of far away. So you can imagine how that would impact climate, right? If you're closer, depending on which side of the Earth is facing the sun at that point, you would heat up a lot more. And if that side of the Earth is now on the opposite end on the elliptical orbit, but it's pointing away, that's a very cold winter. So you have to sort of look at it from that perspective. The next one is called obliquity. That's the tilt of the Earth, which varies anywhere between 22 and 24.5 degrees. If you recall from previous lessons, ours is currently 23½ . And remember, the fact that we have a tilted Earth that revolves around the sun is what gives us our seasons, right? Think about it. January, short days, long nights. June, shorter nights, longer days. And if you head further and further north or south, that difference gets greater. And then finally, precession, which is how the tilt wobbles. So when the tilt wobbles, the seasons are really difficult to determine. They may not be what we think of them as today. So imagine that you're supposed to be facing the Earth, but because it's been wobbling, now you're facing sort of away from the sun. It kind of messes with the idea of how much radiation you get. So combining these three cycles together gives you a sense of how climate can change naturally. Humans have nothing to do with this over long periods of time. Ocean variation. So the oceans act as a mechanism to take excess heat from the equator or equatorial regions towards the poles. And what happens is that warm water heads north, it cools down, it becomes heavy, it sinks, it goes under. Notice how you can see this blue stripe under the red one. And you have this sort of conveyor belt, which maintains the climate as we know it today. So if you mess with this variation in the ocean, you could theoretically change the climate, and you could change it abruptly. This one is, well, kind of obvious if you have an extraterrestrial impact, meaning a meteor. But if that happens, we have bigger problems. Climate modeling. So, models are, one thing about models that you have to sort of keep in mind is climate models are not supposed to tell you what the temperature on October 6, 2070 is going to be. That's not the purpose of a climate model. A climate model is supposed to give you an idea, a general trend over time based on some relatively well understood physical parameters. Okay, so what this tells you here is, so the black is observations, so reality, right? And what the models are showing. So I realize it looks like spaghetti, right? But bottom line, the trends are kind of coincident. Here, what this tells you is, oh, wait, this is climate models reality in black. But if you take away from climate models things like the human interaction, the introduction of greenhouse gases in an artificial way, the Earth really should be stable or cooling down a bit. So what you can draw from that is, if you consider anthropogenic considerations, human considerations, we should be seeing what we're actually seeing. It sort of corroborates the warming that's being experienced since about 1750. Here's another, this is from the IPCC, and this is global mean sea level change relative to 1900. So these are different scenarios, and you don't have to remember what these are. It's just, think of it as scenario 1, 2, 3, 4, 5. Okay, and these are different. It's almost like turning the heat on a stove, right? Low, medium, high, high kind of thing. And so all of them, even the most serene ones, show you that there should be about 0.5 meter increase or up to 1 meter increase. What this dashed line doesn't show or attempts to show is, what if we're really sort of underdoing it? What if reality shows that it's really going to increase upwards of 1.5 to 2 meters in global mean sea level rise? That would literally inundate many parts of the world. So you can imagine what kind of instability that would lead: economics, culture, mass migrations, that kind of thing. And so that's gonna end it. I mean, it's a highly, again, pun intended, changing subject. Lots of new data comes around and comes out all the time. There is another lesson packet from another course that I teach that I made available. It says though that it's testable material, it's straightforward, it simply supplements this. And that's because the book hasn't been updated in a while, so it definitely kind of feels a bit dated, which is why I've tried to update it as many times as I can. Anyway, if you have any questions, please get with me. Otherwise, I wish you well, best of luck, and next week will be the biosphere as we move away from the climate block into a new block. So good luck. Bye.